Have you ever looked up at the sky and wondered what actually happens when a celestial body just disappears? I mean, one moment the sun is beating down or a huge full moon is glowing, and the next, this creeping darkness just swallows it whole. It's a phenomenon that has literally stopped humanity in its tracks for thousands of years. But what's really going on up there in the dark?
Welcome to This Explainer. Today, we're taking a deep dive into cosmic shadows, the mechanics of eclipses. We're going to break down exactly how these mind-bending astronomical events actually work. And we aren't just staying here on Earth. We're taking a trip from our own local shadow play way out into deep space to see how the entire universe gets in on this cosmic dance.
Okay, so here's our roadmap for the journey. We'll start with number 1, the alignment of spheres. Then 2, the anatomy of a shadow. From there, we'll look locally at 3, Sun, Earth, and Moon. After that, we'll dive into human history with 4, from monsters to mathematics. And finally, we'll zoom way out for 5, eclipses across the cosmos.
Let's jump right into section 1, the alignment of spheres. To really wrap our heads around an eclipse, we first have to grasp the basic planetary alignment that makes it all possible. Ultimately, it all comes down to geometry, and the absolute key concept here is Syzygy. It's an incredible word, S-Y-Z-Y-G-Y, and it basically just means the straight line alignment of 3 celestial objects in space. When 3 objects perfectly line up like that, one of 2 things is going to happen, depending entirely on their sizes and how far apart they are. The first is an occultation. That's when one object is completely hidden by another object passing in front of it. The second is a transit. This happens when the object passing in front is smaller, so it leaves the background object partially visible. The coolest part? Every single eclipse you've ever seen is just the spectacular result of a syzygy.
Moving right along to section 2, anatomy of a shadow. Let's see how this actually built.
So our spheres are aligned, right? Now we need to look at the actual physics of how light gets blocked. When light from a massive star is blocked by a planet or a moon, the shadow it casts out into space isn't just one big solid block of darkness. It's actually highly structured into 3 very distinct parts. Step 1 is the umbra. That's the Latin word for shadow, and it's the sweet spot where the object completely covers the light source. If you're standing in the umbra, you are in total, absolute darkness. Step 2 is the penumbra. Here, the object is only partially blocking the light source, so you'd only see a partial dimming of the light. And finally, step 3 is the antumbra. This one happens when you're standing much further back. The object is perfectly centered in front of the light, sure, but because it's so far away, it looks too small to cover the light entirely. That's what creates that famous ring of fire effect. Getting a handle on these 3 terms is absolutely crucial to understanding every single type of eclipse.
Which brings us to section 3, Sun, Earth, and Moon.
Let's ground these abstract physics concepts by applying them to our own familiar neighborhood. Let's compare our 2 most famous local eclipses. First, the solar eclipse. This happens during the day when the new moon sneaks exactly between the Earth and the Sun. It's an incredibly brief event, and it only casts a very narrow path of totality on the Earth's surface. A lunar eclipse, on the other hand, happens at night during a full moon when the moon wanders right into the Earth's massive Umbra shadow. Unlike a solar eclipse, a lunar eclipse can last for several hours, and it's visible to an entire hemisphere of the Earth all at once. But here is what's really fascinating. Even when it's sitting in the Earth's total shadow, the moon doesn't go completely pitch black. Earth's atmosphere actually bends or refracts sunlight into that shadow, scattering away the blue light and casting this incredibly striking blood-red hue onto the lunar surface. It's wild to think about.
Now, let's talk about just how fleeting a total solar eclipse really is. Even under the absolute best, most favorable geometric circumstances, the maximum duration of totality you could ever possibly experience on Earth is just 7 minutes and 31 seconds. That's it! And that shadow's track, the Umbra sliding across the Earth, it's at most 250 kilometers wide. Do you want to know why it's so incredibly brief? Because the moon's shadow is racing eastward across the surface of the Earth at a staggering 1,700 kilometers per hour. When you watch a solar eclipse, you are literally watching a giant shadow move at supersonic speeds.
But here's the crazy part. Despite that wild supersonic speed, the whole thing is deeply mathematically predictable. 6,585.3. That specific number of days, which works out to just a little over 18 years, is known as a serocycle. Because the orbits of the Earth and the Moon follow this repeating harmonic pattern, eclipses actually repeat themselves on this exact cycle. Every 6,585.3 days, the celestial geometry completely resets, giving us a nearly identical solar or lunar eclipse. It's just this brilliant, flawless piece of cosmic clockwork.
Let's transition over to Section 4,
from monsters to mathematics.
Long before we understood the perfect exactness of that Saros cycle we just talked about, eclipses were probably the most terrifying things a human being could ever witness. I mean, just imagine it. Imagine not knowing that the moon is a giant rock orbiting our planet, and suddenly the sun just vanishes in the middle of a Tuesday. Mythological fears were completely rampant. In Norse mythology, people believed that these massive wolves named Fenrir, Skoll, and Hati were constantly chasing the sun and the moon. So in eclipse, that meant the wolves had actually caught them and were actively eating them. Meanwhile, in early Hindu traditions, eclipses were often seen as the work of evil spirits. It prompted people to sing hymns, fast, and wash in the spiritually cleansing waters of the Ganges River just to protect themselves. For our ancient ancestors, an eclipse definitely wasn't cool geometry. It was a profound, divine threat. But over time, humanity observed, we recorded, and we learned. As early as March 5, 1223 BC, a Syrian clay tablet accurately recorded a solar eclipse. By around 500 BC, the Greek thinker Anaxagoras made this massive intellectual leap. He explained that the moon doesn't actually generate its own light, but it shines by reflecting the sun. And by the 5th century AD, the Indian mathematician Aryabhata was out there literally mathematically computing the exact sizes of the shadows cast during eclipses. We evolved all the way from fearing invisible sky wolves to doing the complex math of the universe.
Which sets us up perfectly for Section 5, Eclipses Across the Cosmos.
Now that we've totally mastered our local shadow play, we can zoom way out to the rest of the solar system and beyond. And this is where it gets super interesting, because observing distant eclipses literally changed the entire field of physics. Take Jupiter, for example. It's a massive gas giant with huge moons and a low axial tilt. That means its moons are constantly eclipsing the planet, casting shadows right onto Jupiter's swirling cloud tops. Well, back in the 1670s, an astronomer named Ole Romer noticed something weird. When Jupiter was on the far side of the sun from Earth, these eclipses seemed to happen 17 minutes later than his math predicted. And he correctly deduced that this delay wasn't a math error. It was simply the time it took for the image of the eclipse, the actual light itself, to travel that extra distance across the solar system to reach Earth. So by simply timing shadows falling on Jupiter, he produced the first ever estimate for the speed of light. How amazing is that?
And the truth is, eclipses happen absolutely everywhere. Over on Mars, the moons Phobos and Deimos are way too small to completely cover the sun, so they just create these frequent, tiny partial transits. Out in the freezing, dark edges of our neighborhood, Pluto and its massive moon Charon actually went through this wild period between 1985 and 1990 where they mutually eclipsed each other every single day. Now, Mercury and Venus, they don't have moons, but from our vantage point on Earth, we can watch them periodically transit across the face of our sun. We can even look way outside our own solar system to what we call eclipsing binaries. These are star systems, like Algol, that consist of two stars orbiting a shared center of gravity. When one star passes in front of the other from our perspective here on Earth, the total brightness of the star system visibly dims. Eclipses really are a universal mechanic.
To wrap up this explainer, I want to leave you with this fantastic thought from American author Gene Weingarten. He said, and I quote, "I am a devout atheist, but can't explain why the moon is exactly the right size and gets positioned so precisely between the Earth and the sun that total solar eclipses are perfect. It bothers me." When you really stop and think about it, the fact that our tiny moon happens to be just the exact right size and at the exact right distance to perfectly mask our massive sun during totality, it's a mind-bending geometric coincidence. It transforms what is just a simple physical shadow into arguably one of the most awe-inspiring events a human being can ever witness. So, next time you look up at the night sky, remember the clockwork of the spheres moving out there in the dark. And ask yourself, what else is lining up out there right now?